Newton's second law. Newton's first law talks when the forces add up to be equal to zero. The net force is zero. In the case when the forces do not add up to be equal to zero, we now say that the sum of the forces is proportional to the mass times the acceleration. Okay? So now we are going to see an object change its motion. An object at rest will tend to begin to move when the net force is not zero. An object in motion will tend to change that motion when the net force does not add up to be equal to zero. Acceleration is the rate at which the velocity changes. So acceleration is telling you how the motion is changing. Acceleration may be a change in direction of the velocity, it may be a change in the magnitude of the velocity, the speed, or it can be a change in both. In any case, when we apply a push or a pull on something, the more mass it has, okay, the more force it will take to change the acceleration of an object. Another way of writing Newton's second law, F equals ma, is to write it as A is equal to F over m. Notice the sigma sign again means net. What is the total force? Also note that acceleration and force are both vectors. So if you want to change the motion of something, acceleration is how much the motion is changing, put more force on it and the acceleration will be greater. With more mass, the acceleration becomes less for the same amount of force. Again, the units for force are the Newton. By Newton's second law, F equals ma. The units for mass are the kilogram. The units for acceleration are the meters per second squared. So when we combine all of them and we get the Newton, it's 1 kilogram times meters per second squared. US customary units are the pound. A Newton is roughly between a fifth of a pound and a quarter of a pound, whereas the pound is about 4.45 newtons. So there's sort of a factor of 4 or 5 between the two. More precisely, there's about 4.45 in factor. If you want to go from newtons to pounds, divide by this, because pounds a bigger force unit. If you want to go from pounds to newtons, multiply by 4.45. Now, again, forces cause changes in motion. They're the ones that create the acceleration. Motion can occur in the absence of force. Okay? Something's moving, can keep moving. But we're talking about change. All forces acting on an object are added together, and that net force will be proportional to mass times acceleration. And again, very important to recognize the sigma. Every force that acts on the object will contribute to this term. This is the sum of every single force acting on it. This is equal to the mass times acceleration. Consider an 80 kilogram person. We'll just do the calculation of the magnitude. How much force would be needed to achieve an acceleration of 2 meters per second squared? We're talking about net force. What's the total force that we need to get an 80 kilogram person moving with an acceleration of 2 meters per second squared? We're changing the motion at 2 meters per second squared. Very simple. Sum of the forces we're looking for. Mass, 80 kilograms. Acceleration, 2 meters per second squared. 80 times 2 is 160. Kilograms meters per second squared is equal to the newtons. So I would say for an 80 kilogram person to accelerate at 2 meters per second squared, we need a net force, a total force of 160 newtons. Okay? I'm about 80 kilograms, so I've got about 160 newtons pulling down on me. But I'm not accelerating. Why? Because weight pulls down and the normal force from the floor pushes up. 160 minus 160 equals 0. This again is the net force. Again, think about this. Calculating acceleration is really taking the sum of the forces and dividing it by the mass. If you want to maximize acceleration, make that the net force as large as possible. Here we do a calculation of acceleration. We have a 1,500 kilogram car, and the engine is producing a force. If we take all the forces of friction, acting against it and the force of the car engine pushing it forward. Let's say we get 2,000 newtons. What is the acceleration? Again, we're treating this as a scalar, so we're just looking at the scalar value. Net force divided by mass, 2,000 newtons divided by 1,500 kilograms. That car is going to accelerate at 1.3 meters per second squared. Gravitational force. Most of the time, when we talk about gravitational force, when we talk about weight, we're talking about objects near the surface of the Earth. We can use Newton's second law, force equals mass times acceleration, to find the weight of an object. Force, weight, is equal to an object's mass times acceleration. In this case, it's the acceleration of gravity. Newton was able to discover that gravity in the more general form, okay, depends not just on the object that's being pulled on, mass of one object, but also the object that is pulling on it. Now, this equation we'll talk about more later on. This is Newton's universal law of gravity. In most cases, we don't have to worry about the force of gravity due to other objects. That's because in this equation, Earth's mass is about 10 to the 24 kilograms. Any other object that we come across is nowhere near the size of the Earth. So the main force due to gravity that we ever experience is simply the force due to the Earth's gravitational pull. A human is a few tens of kilograms. Most of the objects that we come across might be 100, 1,000 kilograms. Okay? So at most, maybe this is 10 to the 5th or 10 to the 6th in kilograms. Nowhere near 10 to the 24. This constant right here, which is the universal law of gravity, is not little g. Little g is 9.8 meters per second squared. Big G is 6.67 times 10 to the minus 11. Okay? It's a really tiny number. So the only time we've got to worry about gravity, other than the Earth's gravity, is if we're talking about a really massive object. A moon, a planet, okay? Maybe even a star. That's the only way you're going to get an appreciable force of gravity. So, talking about gravitational force, we're usually talking about the weight near the Earth's surface, again, due to the acceleration of gravity at 9.8 meters per second squared. So weight is a special case of Newton's second law. Weight is force times, the force of the weight. Weight is a force here is the weight, is equal to the mass of the object times we use the acceleration of gravity. Sometimes you'll see it written as W, sometimes you'll see it written as F subscript G, okay? Usually in high school, physics will use W. Sometimes in college physics, which is algebra based, we'll use W. Sometimes in both calculus and non-calculus college physics, we'll use F sub G. Okay, it just depends on what we're talking about here. But again, here's Newton's second law, F equals ma. We convert that to Fg, or W equals mg. This is a common force that we'll be calculating quite a bit. Again, 80 kilogram person times the acceleration of gravity, 9.8 meters per second squared. How much weight did he have? About 780 newtons. Okay? So if you want to calculate the weight, which is acting on a particular object, know its mass, and just multiply by 9.8 if it's on the surface of the Earth. Again, converting weight, we can use 4.45 or we can use 0.2248. This is the reciprocal of 4.45. If we want to convert 700 newtons into pounds, we multiply by 0.2248. If we want to convert this using the 4.45, we divide by 4.45, and that gives us back pounds. Again, pounds are the larger unit. Now to convert from pounds to newtons, we divide by this, or again multiply by 4.45. Can't stress this enough. Weight is not an inherent property or an intrinsic property of an object. Okay? Mass is. How much matter is in an object is its mass. For instance, an astronaut in a spacesuit might have a mass of 100 kilograms. Okay? What they weigh depends on location. If you're on the surface of the Earth, it's times 9.8. So they weigh 980 newtons. If they're on the moon, the acceleration of gravity on the moon is 1.7 meters per second squared, 1.62. So they weigh 162 newtons. Where you are will determine what the gravitational field is, and it's mass times acceleration of gravity, which gives you the weight. Let's do a good illustration of Newton's second law. Okay, here's what we have to think about: sums of forces. The Delta IV Heavy is now the highest capacity rocket in production in the United States. I don't know if that's true with the Falcon 9 Heavy, but they're pretty close. Okay, I think the Falcon 9 Heavy can put something to low Earth orbit with more mass. This can boost it to geostationary orbit. Can put more mass up there, so they're sort of different. This uses hydrolox, liquid hydrogen and liquid oxygen, so it's a little more efficient than the Falcon 9. Not reusable though, so once you use this rocket, it's done. The Falcon 9 can at least land. But it consists of 3 cores, each with an RS-65 engine, and each engine generates a thrust of 2.89 meganewtons, million newtons, for a total thrust of 8.67 million newtons, meganewtons. Okay? So you're like, oh, okay, the rocket has a mass of 750,000 kilograms. It has a thrust, upward force of 8.67 million newtons. I'll just, to find the acceleration, take force divided by mass. You'd be wrong. You have to take into account that this is not weightlessness. You have an upward thrust of 8.67. You have a downward weight of 7.35. If you take this mass and multiply it by 9.8, you get 7.35 million newtons. Okay? So the net force in doing this calculation on liftoff is 1.32 million newtons. What is the rocket's acceleration? Well, given that our net force is 1.32 and that our mass is 750,000, 1.32 million divided by 750,000, okay, newtons divided by kilograms, gives you an acceleration of 1.76 meters per second squared. Now it's important to note that this is the mass at takeoff, okay? As it burns fuel, and this thing goes through a ton of fuel. Now, actually, a ton is sort of underestimating how much fuel. This burns through fuel at an incredible rate. These tanks empty in a matter of minutes. Okay? Not many minutes either. So as it goes up, this mass gets smaller and smaller, and it actually begins to accelerate faster and faster. The rate of acceleration increases as the velocity gets greater and greater per unit time. So this is the acceleration at liftoff. As it's further up, and if the rockets are still operating at the same amount of force, it's accelerating faster. By the way, I gave you a very rough estimate. On takeoff, all 3 rockets are burning pretty much at the same rate. The center rocket will then throttle down. You can actually see the outer boosters are a little more, a little brighter. The center throttles down to conserve fuel, so the outer boosters will burn up first. They will detach. You'll only have the center core, and that'll take the rocket the rest of the way. Again, the Falcon 9, called Falcon 9, do you know why? 9 rocket engines. Each rocket engine produces a little under 1 million newtons of force, or 850 kilonewtons. So 9 times 850 gives you 7,650, or 7.65 meganewtons. Looking at this has a little more thrust than the Falcon 9, But when you consider if you strap 3 of these together, you get an even more powerful rocket. Again, Falcon 9 Heavy can boost more payload into orbit because it has, about 2.5 times the takeoff thrust. In any case, this is a reusable rocket, and what's cool about this is it'll accelerate upward. All 9 engines will be on for this maximum thrust. It'll be fully loaded with fuel. But a rocket is mostly fuel. If you look at the total mass of the rocket, it's between 80 and 90% fuel. So after it's done its mission and it's taken the second stage and payload to where it's supposed to go, this is actually the Dragon crew capsule up at the top. This top part will break off, will detach, the second stage will ignite, and the first stage booster will return back to the ground. Now here's the thing, they only need 1 engine to land. Why? Because if 80 to 90% of the mass of this rocket is gone, it's fuel, right? Most of it's gone. Even a single engine is almost too powerful for it to land. So watch a Falcon 9 land sometime, and it's basically falling in an ignitous rocket pretty close to the ground. We call this a suicide maneuver because it looks like it's going to crash, and at the last minute the rocket goes off. Because if the rocket engine ignited too soon, it would actually end up going upward. Before landing on the ground. So again, that's SpaceX's rocket. Here's another example. We have a propeller boat with a mass of 350 kilograms. It's going to experience a force of 770 newtons. Okay? So the net force is equal to mass times acceleration. We want to find out what the acceleration is. Okay? We assume the acceleration is constant. Force divided by mass. Net force divided by mass. 2.2 meters per second squared. The interesting thing is, once you have the acceleration, this becomes a constant acceleration problem. If the force is constant and the mass are constant, we have a constant acceleration, and we can use the kinematic equations for constant acceleration to solve this. Let's say we want to know how long it takes to go from 0 to 12 meters per second. We want the final velocity to be 12. We want the initial to be 0. We know the acceleration. We want to calculate time. 5.45 seconds for this to accelerate at 2.2 meters per second squared and reach 12 meters per second, or roughly a little more than 25 miles per hour. Okay? After reaching the speed, the pilot turns off the engine and drifts over a distance of 50 meters. Find the resulting net force. Here we're going to go the other way. We're going to say it's going to come to rest, but it's going to start at 15 meters per second. It glides at a constant acceleration of 5 meters, and its mass is 350 kilograms. We want to find the acceleration and therefore the force. So we know v, we know v0, we know x, we know the mass, we don't know time. Time's not in here. We're trying to find a, so we use the last kinematic equation. Solve for a, the acceleration slows down at a lower rate than it's sped up, negative 1.44 meters per second squared. We then use the acceleration, force is equal to mass times acceleration, to find out the force of drag, negative 504 newtons, negative because it slows it down. So pretty cool that we can use, if the acceleration is constant, the force to find the acceleration and the acceleration to find the force. Understand that force is a vector. If your force and your acceleration are not necessarily in the same direction, we've got to resolve the vectors. Here we have a boat which is going to move in the x direction, but it's being pulled at an angle, F1 and F2, which are theta 1 and theta 2 above and below the x-axis respectively. How do we do this problem? Well, we've got to resolve this vector and resolve this vector. Okay? Here's force 1, here's force 2. Here are the angles. Find the x component, add it to the x component. Find the y component of F1, add it to the y component of F2. So what we do here is we're finding net force. But you know when we add vectors, what we need to do is resolve them, add the x's to the x's, the y's to the y's. Okay? We find the x force and the y force. Knowing the x force and the y force, we can now find the acceleration. In this case, I'm finding the acceleration in the x direction and the acceleration in the y direction. I could have just found the total force and found the magnitude of the acceleration, but I want to find x and y components here. And once I have the x and y components, then I find out the total acceleration, or the magnitude of acceleration. So this barge is going down the canal. It's accelerating at 0.476 meters per second squared at a slightly lower angle than 0. It's going toward the right shore a little bit more. So I guess gets centered better. But again, this illustrates a typical problem that you do with Newton's second law. Okay? Identify what your forces are. Okay? Find their angles. Once you have the magnitude of the force and the angles, resolve them. X and Y. X and Y. Find the X and Y components. Cosine for X in this case, because we're doing it with respect to the x-axis. Sine for Y. Okay? Each angle is different. Again, notice this angle is negative because it's below the x-axis. Add the x forces together, the y forces together. Once you've done that, acceleration is force divided by mass. Okay?